Yep.
All right, hello everybody. Today I have with me here Philip Rowse. Philip is the CTO of CubePilot, and Philip has been around almost from the beginning. Philip actually joined the core team of Pixhawk Autopilot system during Pixhawk 1, and then has helped to develop the Pixhawk hardware. And with his background in avionics, he has been part of the team and developing this #1 leading autopilot system that we have today. Hello, Philip.
G'day, how are you?
I'm good, thank you. So do you want to tell me a little bit about the background, how it all started, and sort of how all the bits and pieces come together?
Yeah, no worries. Well, I actually got into ArduPilot. It would have been about 2011 that I started playing around with it. I was actually good friends with one of the founders of OpenPilot. And he, at the time, when I was doing a project and needed an autopilot, he advised me to actually join ArduPilot. As many open source projects are quite friendly with each other, he saw what I needed and sent me to ArduPilot, and that's how I got into that team. In 2013, I actually ended up with some time off work because I got sick, and I was bored and knew at the time that the ArduPilot team was looking at playing around with Linux as an autopilot. And as I was bored, I thought I'd design an autopilot for the team, and we did the PX4 autopilot, and that became quite a useful tool. And in the process, that brought me to the attention of 3D robotics, and we were talking about the Pixhawk 2 at the time, and basically what was going to follow from Pixhawk 1. We still had to do a fair bit of work in setting up Pixhawk 1 and getting that finalized. And yeah, so basically, actually, I'll probably get you to go to the CubePilot website. The Profi CNC website is becoming null and void soon. We'll be depreciating it. Yep. So that's our new website there. So yep,
That's
awesome. A bit fancier, a bit more up to date. It gives you direct links to all of our support and all of that sort of stuff as well. So sorry. Yeah. So
I have a question about so I remember OpenPilot. I remember ArduPilot was one of the first. And how did the PX4 firmware came about? What was the idea behind that?
Okay, so look, I mean, if you want a background of PX4 firmware, you're probably best to get Lorenz in here to have a bit of a chat. But
okay, right.
The long and the short was Lorenz was doing some wonderful stuff with ETH University, and he needed a flight stack to go with that, and he started developing what became the PX4 autopilot system. ArduPilot and PX4 sort of teamed up at when the PX1 autopilot existed, and they actually ended up cooperating to do what was the Pixhawk 1, and that's when the ArduPilot hardware team, which I'm a part of, and the PX4 hardware team joined forces and developed the Pixhawk 1. So you actually have two very separate autopilots, and actually quite separate philosophies in open source. Both of them are open source, ArduPilot and PX4. One of them is a BSD license, which is PX4, and ArduPilot is a GPL v3 license. Quite different philosophies in why the licenses were chosen and what that means to the project, and it's quite it can be a contentious issue at times in selecting which flight stack you want. Often the license is actually quite a prominent feature as to why people will select one over the other.
So was that somehow related to the willingness to try Linux on this hardware, and was that a part of how PX4 also came about, or was it just somewhere on the side like PX4?
No, the Linux attempt yeah, the Linux attempt was more on the ArduPilot side of things.
Okay.
So we got the flight stack ported over to Linux on the PXF. First, we actually got a Raspberry Pi with a couple of various sensors on board to behave as an autopilot, and that was pretty cool. And then we designed an actual board based on the BeagleBone Black to do some flights there. Andrew Tridgell actually demonstrated it while we were in the US, actually commanded the aircraft from the United States, took off in the US and did some various flights while also compiling Linux on the flight controller while it was flying in Canberra while he was in America, which was pretty impressive at the time. That was back in, I think that was 2014 or 2015. I'm not quite sure. It's a while ago now, anyway. So that was very much on the ArduPilot side of things. So most of my experience is on the ArduPilot side of things. Part of the ArduPilot development team, and yeah, my experience is definitely more on the ArduPilot side than the PX4 side.
Right, and you have been you joined the team during the development of the first Pixhawk Autopilot, but that didn't have a Linux computer attached to it, right?
No. So, well, the Pixhawk 1 and all of our current autopilots don't have a Linux computer attached to it.
Yeah.
We moved, one of the things that the whole Pixel Fire or PXF project actually showed us was if you want an autopilot to be a really good autopilot, build an autopilot. If you want a vision system to be a really good vision system, build a vision system. Now, they might end up being physically on the same board in an aircraft that needs to be nice and small. You know, a great example would be something like the DJI Mavic or something where you don't have much room on board to put lots of devices all over the place, so you sort of build it in together. But even on something like that, the autopilot is the autopilot, the companion computer is a companion computer, and you allow the aircraft to use the appropriate resources to do the right thing. Even though we successfully flew on Linux, the problem is you needed to put the flight controller at the highest priority. So if you really wanted to do really good vision, you had to do that in the background, and you had to have, you know, secondaries. It had to be the secondary process. So it just wasn't so critical to do all your vision. Now, if you look at things like, I'll use the Skydio as an example. If you want to do something where you're doing incredible vision navigation, you really want something dedicated for that purpose. And the same for an autopilot. You want the autopilot to be able to just be the autopilot. They may interact and they may completely rely on each other's data, but you still need it to excel at what it's good at. So we moved more to a modular framework. So the Cube is a autopilot on a module that basically, depending on how you want to use the thing, it plugs into any sort of carrier board or any sort of aircraft that needs it. And some people will have a companion computer on that, other people won't have a companion computer on it. So the tie-in with Linux, though it makes sense to use it for onboard systems, just didn't quite make sense for using it for the autopilot itself.
Right. So you have the Cube for the autopilot, and then you can have different carrier boards that basically implement all the connectivity. So what was the first thing that you did when you joined the team? So you have experience in avionics and sort of professional systems, and then when you joined in the beginning, it was there was a lot of hobby stuff going on in the autopilot industry. So what was the first thing that you wanted to improve in this project, and what did you improve? What did you end up sort of revolutionizing?
Yeah, well,
on the side?
Well, I suppose the first thing was, you know, ensuring redundancy. I mean, the Pixhawk one actually did have a certain level of redundancy, but it wasn't there for the point of redundancy. It was there because a choice had to be made as to which sensor suite to put in there, and a couple were put in to make a choice between. And during the development, that became quite crucial because we actually found a problem with one of the sensors, and we found that the other sensor actually behaved better in certain circumstances, which actually meant that by fusing the data correctly, we could actually get out of situations that would have otherwise led to a crash of previous hardware. And we
So
wanted to take
what was the actual situation? What was happening? Was it the magnetometer that?
No, this was the accelerometers aliasing at 1,000 hertz, and
Right.
basically we had on board an LSM303D and a MPU 6000, and the LSM303D had a nasty alias at 800 hertz, and the MPU 6000 had one at 1 kilohertz, which is quite convenient because it means that at either frequency you had one behaving really well. So the basic start of some failover logic got put into ArduPilot at this point, and also into PX4 by default at that point. And that was sort of the beginnings of using that hardware. But even though it was there, it wasn't really by design. And then we really started focusing on that redundancy. And when we designed the Pixhawk 2, otherwise known as the Cube now, we put in triple redundancy, and we also added the vibration isolation. But in the process, we looked at, you know, the failure modes that this could then bring about. The minute you have something that is isolated, it comes with negatives. There is a consequence for putting something on a flexible structure, and that is there is a resonance that goes with that and a natural frequency. So if we were to put all three IMUs on the isolated board and we hit this natural frequency, there's no way for the autopilot to actually know that, hey, that's an onboard natural frequency. It's not what the aircraft's actually doing. Therefore, you know, yeah, so you could end up leading to a crash if you didn't take that into consideration. So on the
natural frequency would be the sort of when you place this on little rubber standoffs, the way that it vibrates side to side by itself, right?
Yeah. So at a particular frequency, well, a good example would be a wine glass. You know, you flick the wine glass and you hear a tune. Yeah. You hear a tone that is of a particular frequency that is the natural frequency of that glass. Now, if you then inject that frequency at a high enough amplitude, you can, you know, shatter the glass, which is quite a good science experiment for high schools. But that same thing applies to anything that has a harmonic. That if you enter that frequency into the system, you can cause it to fail. So by having the first layer of defense was having the two different IMUs sampling at different rates. So we could deal with the 800 hertz, the 1 kilohertz, and then by putting two IMUs on the vibration isolation and one fixed one, we could eliminate the natural frequency of the vibration isolation and give us a ability to fall back to the other IMU while in those situations. So as time went on, we increased the sampling rate of the sensors, and that basically got us out of the problem of the 1 kilohertz and the 800 hertz issues that we were having on Pixhawk 1. And also the first versions of Pixhawk 2 had those same sensors on board, so it had the same risks, but they were eliminated by mechanical design and electrical design. So it's really a combination of getting the software right, the mechanical design right, and the electrical design right, and getting that all together and working as a team. And that was a real advantage we had working with the ArduPilot team. sorry about that.
No problem.
That was a real advantage we had as working within that team, is the hardware, software, mechanical, all working together to come up with a autopilot solution that covered these risks off. Yeah, and then obviously as the time goes on, we find any other little quirks that are in the system. I know with Pixhawk 1, we found some power up issues that were causing problems in certain people's vehicles. One thing that really hit home to me early on was when we design avionics for a full-size aircraft, we design it for one aircraft in one circumstance, wired a particular way, and everything is checked. When you're designing stuff for a hobbyist, you have no control over what they're going to do, how they're going to do it, where they're going to do it, what they're going to plug in where. We found all these little side cases of, people putting digital servos into the servo rail and, the wind causing a servo to move in a way that would suddenly inject a high voltage into the servo rail and shut down the flight control system. And, so we added Zener diodes on servo rails, and then on, Pixhawk 2, we eliminated the servo rail out of the power system for everything other than an absolute last resort. And, all of these learnings that come along over the years get gradually brought in and brought in and brought in. And you end up with a flight control system that is really robust and really solid. So, yeah.
So one of the decisions that you guys made was to have two processors. You had an F4 and you had a F1, I think, for the iOS.
Yep.
What was the logic behind that? Why not just put everything on the F4?
In the early days, I mean, that was very much legacy from the PX1, where we had the flight management board that had a certain amount of channels, and then people wanted more. So rather than changing the whole way the flight management unit worked, an I/O board was added to give extra channels, etc. And ironically, now we actually call channels 1 through 8 the main outputs, and we call the FMU ones the auxiliary. It's actually technically the other way around, because the I/O board is the auxiliaries and the FMU is the one attached to the actual flight management unit. So that was originally a legacy, but then because it was there, in plane especially, code was added to be able to cope with the main flight controller failing. So if the main flight controller failed, you could actually ensure that outputs went to a particular state. Say parachute was triggered, or it went to RC pass-through, so that the remote control could just go into manual mode and take over and rescue an aircraft, release a parachute, or sound an alarm, or do whatever's necessary for that final stage of flight where you have no flight computer anymore. So it added a fail-safe level that over the years is becoming less and less and less necessary, because the code is becoming more and more and more robust. But there are quite a few applications where people want multiple flight controllers in the mix. We have situations where people are running, 3 cubes, and they're switching over between them, and they're actually using some of that logic on the I/O processor to do that. So that's sort of stayed. I know some of our competitors have got rid of that chip. I know on the racing side of things, people, don't use the features of that, and it does add a little bit of latency to the outputs. So if you're doing a racing drone, obviously that's a bit of a pain. But the benefits for those that do need it are well worth it.
Okay. So in terms of hardware, what were some of the challenges that you guys faced? Because it's such a magnetically saturated environment. You have the motors, you have the noises from all the power switching that's going on. What were some of the
Yeah.
challenges in that, and how did you solve them electrically? So you mentioned,
Yeah,
you
well,
mentioned the combination of software, mechanical, and electrical. I'm curious about the electrical part there.
Yep. Well, one of the first things was defining a rule that autopilots are not power management systems. I still get questions from many of our customers, why don't you do this or why don't you do that? And my answer is because I don't control your airframe. Why don't we make our power module, for instance, ready to take 400 amps? Well, the reason is because most people don't need that, or if you do need something like that, you need to consider your whole flight system and your whole aircraft design when you design that. It's actually very hard to design a universal solution for absolutely everyone. I held this up before, which is a flight control board for a 450 size drone for education market. And we've got boards like this one from Basque Aerospace for controlling a rover that also there we go, plugs the cube in over here. Each of these applications has completely different electrical needs and priorities. So really, by taking the autopilot out, taking the electronics of power out of the autopilot and allowing that to be something more related to the carrier board was sort of step one in that. Step two was try and make the critical power management easy for anyone. So we made this little board here, which there's a version of this in the Pixhawk 1, which is a power management unit that selects the best voltage for the actual flight controller and controls current to the accessories. Now, it always prioritizes the flight controller as absolute. We can lose GPSs, we can lose everything else, but we don't want to lose the flight computer, so we prioritized on that. We added into that a Zener diode, a fuse, and a few other things to prioritize the auxiliary input that can be connected to servo rails and things like that to automatically disqualify itself if certain parameters were breached. And we did that in a way using analog electronics to try and make sure there was no software in that loop whatsoever. So its behavior was very predictable from system to system to system, and tried to make it as versatile as possible. So we kept that modular sort of thought about it. Power management is here, flight control is here, and you can't solve every problem. It's just reality. If you don't know the person's overall system, you can't solve the problem for them with no parameters. That was a real focus. And since we did with 3DR, we did the 3DR solo, and we learned lots of things about how not to do power management on that one.
Like what?
And we've been involved. Well, we had some fun things with ESCs that didn't behave themselves on that, and we learned our lessons there. And when we obviously continued after the post 3DR days, we incorporated that knowledge into the Cube. So we had a Cube Green that was specifically designed to fly in a 3DR solo to fix the hardware problems that were in the solo, so people could upgrade and keep going and get extra performance. And then we incorporated that into the Cube Orange as now a parameter. You can select your PWM voltage levels depending on what accessories you've got to ensure you've got the best signaling for what you're connected to or the airframe you're in. So each time we find a problem in someone else's airframe that we haven't thought about before, we try and figure out how do we make it more robust for them in the future.
So how do you do a lot of simulations, or is it mostly physical testing through actual aircraft that people are flying?
Um,
Or is it mostly community that tests the hardware?
it's mostly community. We have a test crew over in China that do a hell of a lot of flying on a daily basis, verifying things. If there's something that we change, we get that tested over there before anything goes public, or we put a flight controller on someone's desk. We tend to make sure it's been flown at least a few times before the developers get a hold of it. Sometimes that's not possible because, if we've developed a new piece of hardware with a new sensor that needs new code, sometimes the developers get a hold of it first to get code. And normally within the open source team, you can tell someone that it's not ready for flight, but if it's sitting on their desk and they want to go flying, you might get that first test flight well before it was scheduled to be done.
Yeah.
So, yeah.
I mean, what I find really, really cool is that all of this is completely open hardware that people can see and modify. And yet you guys have been able to build this into a commercial product that is really high quality and really successful. What were some of the lessons that you learned from that? And how do you think that open source helped you to kind of propel this into the mainstream?
Yeah, well, it's a complex issue, that one, because
Yeah, it's quite complex. There's so many licenses. There's different ideas about how to actually go about doing it. But like from your experience, where do you think the positive points are? Where do you think the more problematic points are?
Yeah, I suppose I went into this project, unaware and very naive, which was probably good, because if I knew all of these problems that we would have had, knew the challenges, and knew that, what are we, 8 years after? No, 8 years after I started Pixhawk 2, now, and 8 years, 7 years. If I knew how long it was going to take to get it to the point that it is what it is now, I'm not sure I would have started the journey, to be honest. But at the same time, without open source, it wouldn't have started either. I mean, I wouldn't have had the guts to jump in and try and find funding for millions of dollars worth of development of the software to start with, and then all the prototypes of various hardware, and trying to develop a product for aviation without a path or a business plan would be impossible without the jumpstart that open source gives you. At the same time, open source is sometimes a two-way street and sometimes not. When it comes to software, when people are contributing back and forward, there's ongoing benefit as long as everyone's open with it. With hardware, there's significant expense in developing hardware and getting it to the right place and making it reliable. Getting people to trust your product is very difficult. It takes years of proof that it's reliable, and then all of a sudden things can go wrong. We had a situation at the beginning of 2019 where we grounded 6,000 cubes. We put messages out on the ground control stations when people booted up and said, your cube's affected by a service bulletin, don't fly. That was super expensive and really blew a big dent in what we finally thought was, yay, we're finally making a profit. And, oh, no, we're not. So, things happen, but being honest with the community is something that is actually really easy to do when you're an open source group, because yes, you're honest with the community about the problem, but the solution in the software side of the solution is 100% transparent. So therefore, it's pretty easy for the community to say, oh, I see, they've done this, this, and this to mitigate it. And this is why I can trust it moving forward. And that honesty in the open source community is absolutely critical. I see people trying to add a bit of political spin onto why they screwed something up, and it backfires, especially when we're talking aviation. You can't. You've got to just tell people the blatant truth. You know, you can sugarcoat it a little bit and say, you know, and we've got a solution coming, but you've got to tell them the truth in the first place. You can't do anything other than that. So that's difficult, but in the long term, it pays off, because people then believe you when you say, hey, it's working now. People then trust you, which is good.
And all of that is accessible to everybody, for everybody to see, right? So if there is a hardware bug, then they can look at the schematic and it can be pointed out that here is a hardware bug and now we fixed it. So they can kind of see the whole process.
Yeah, it's actually, though, I would say when I'm looking at disappointments on the open hardware side of things, I would actually say that's probably my biggest disappointment, is that I don't have more people doing that. I would say I could name the people that have actually given me constructive negative feedback. I mean, I've had plenty of customers that just don't like the product and will quite happily bag it out. But as far as constructive negative feedback, in as far as, okay, I looked at your schematic and this and this and this is wrong, do you reckon you could fix that next time you're doing a spin? I'd probably say we're at 4 people. And in a community as big as this is, that's actually sad. When you consider that we have, you know, dozens of companies that have grabbed our schematics and our drawings and have made their own products and are directly competing with us with those products, that aren't really contributing anything back. Some of them have opened their drawings, but I don't have a single pull request from any of those competing companies, which that's a bit disappointing, but you know, it's a risk. There's enough benefits to the open that, as much as some days I get a bit frustrated with some of our competitors, I have to step back and go, you know, I wouldn't be here if this wasn't all open in the first place. So yeah,
that's really interesting. So how just to get an idea of the scale, so how many people, how big is the community in total, would you say? I mean, it's impossible to say, but kind of like your guess.
Millions. Like if you look at the download statistics on ArduPilot, like I don't have the download statistics for the PX4 side of things, but you know, the millions of people and millions of downloads of ArduPilot on Mission Planner is just incredible. This is a project that has just been from people who are interested and work together and get along, and you know, there's some great friendships and just lifelong bonds with all these people, and it's turned into something that's now delivering kidneys and eyeballs and hearts, and you know, delivering aid. You know, we've got our autopilots, you know, DHL, UPS, Swiss Post. They're all cubes in all of that, and all of that wouldn't have happened if it wasn't for, you know, Jeff Wurzbach being really busy in doing Pixhawk 1, and Craig Elder giving me a call and saying, you know, I like what you're doing, you know, you want to come on board and we'll get 3D Art to sponsor your work. Like, it's all just people communicating and getting along in a community, and yeah, it's quite incredible.
Cool. So millions of people and only 4 people understand what it actually does on the deep level.
Look, I mean, there'd be more than that, because there's plenty of people that are obviously using it for their own products and stuff like that aren't contributing back. But but on the software side, the community is actually very active. And the thing I love about ArduPilot with the GPL code is the companies that understand GPL really do very well out of it. You know, there's especially startups with VC funding and a few lawyers sit there and say, what do you mean you have to give your IP away? And it's just looking at it the wrong way around. What they have to look at is, what do you mean we get tens of millions of dollars worth of IP for nothing? You know, you've got to turn that question around. And you know, you might come up with this little tiny little special function of secret source that you've got, and by contributing that to the open source community, that goodwill that you give is returned 100-fold with this bug fix and that bug fix and that thing there and that thing that makes your vehicle better. And, you know, we've got people, we've got a guy in England that's just added a whole bunch of FFT stuff to take the last little niggles out of the autopilot in as far as vibration tolerance and stuff like that. Now, everyone gets that for free. And it's just given, and given, and everyone wins. So overall, I mean, you want to build a drone, you want to do something incredible in the UAV industry, the flight controller is done. You don't have to spend your millions of dollars worth of VC funding on that. You leave that to us on hardware, leave it to ArduPilot on software, and just focus on building the best unmanned system that's out there, and you know, we'll keep it in the air for you. And that's sort of where we're at now.
So how did it affect you from the business side of things that you have open hardware and other companies, which maybe your competitors take it and basically do their own stuff? Yet you are still sort of the most popular, right? So something you must be doing right. So what is the dynamic there?
We don't take any shortcuts when it comes to quality. We test everything. Our Cube Orange goes through a full motion test jig in the first place, gets programmed up, and every I/O gets tested, blah, blah, blah. Once it's past that, it goes on to an aging jig in an environmental chamber. It sits in that chamber for 3 days and is brought down to -20 and up to 70 and back and forward and back and forward and back and forward, and aged for 3 days in pretty nasty conditions. And then it goes through a final jig that then goes and analyzes everything to make sure that it's genuinely happy and it got through each of those cycles without giving any grief. After that, it gets packed and sent to our customers. And you know, this testing takes a lot longer. The most expensive part of our board is not the bill of materials, it's not the manufacturing, it's actually the testing. And, you know, it gives us a product where, number one, we're confident by the time it goes out the door that it's good. And if something does go wrong, we can find out why later down the track and, you know, add that to our testing and make sure that doesn't happen again. So we put a lot of effort into that side of things. You know, don't get me wrong. I mean, our competitors are, you know, it's a small industry and there's a lot of players. So that's a real issue, and we have to constantly stay on our toes. And I mean, that's good because competition means there's better products for everyone. So, you know, we don't want it to be too much competition, but
yeah,
it's just, yeah, people vote with their feet.
Yeah, I know you have a meeting in about 6 minutes, but I have a last question here. So if you were to do this all over again, would you still make it open hardware?
Ooh. I went through a stage probably about a year and a half ago. I had various things going on in my personal life and a whole bunch of other stuff. And to be honest, the open source community got to me. And I was to the point of saying, no, stuff it. You know, we had all these hardware competitors, one that really directly competed with the whole concept of the Cube. Won't take anyone much guessing to figure out who that was. And then they claimed they designed it from scratch. And, you know, I just had that moment of stuff, a lot of you. Let's go closed. And, you know, we actually sort of investigated down that path, and it was a stupid thing because, you know, we looked at what would it take to go closed. And it doesn't matter how annoyed I am at one of our competitors or someone in the open source community annoying me. We literally worked out we've got hundreds of millions of dollars worth of engineering resources at our fingertips with this team. We don't, I mean, we sell our autopilots, you know, for a standard cube with, you know, ADS-B, blah, blah, blah. It's $250. We don't make enough money on this by any stretch of the imagination. The industry is not big enough for us to even think about funding a closed version. It's not going to happen. So we're actually under a fair bit of attack at the moment from a autopilot manufacturer who's been around for many, many years with a closed system. And we're actually finding it really complimentary that he's attacking us, because all of a sudden our open system is being used by massive entities around the world, and we're actually putting the closed systems at risk. And it's just reassured me over and over and over, no, open's the way to go. There are definitely drawbacks to it. We don't get approached by VC funders because VC funders want their own IP. Yeah. But we also owe nothing to anyone. So, you know, start slow, do it slow. Don't bite off more than you can chew, and be honest to your customers. Open source is awesome.
So you would do it open source and open hardware from the start if you were to do it all over again?
I would. I'd probably have a few hesitations in the middle, but I'd still do it. Yeah.
Okay. Awesome, Philip. All right. It was great talking to you. Let's keep in touch and see if there is anything else we can explore later on this topic, because it's such a vast topic and it's so interesting to kind of explore it with somebody who's been around for a while.
Thank you very much for having me.
Yeah.
Much appreciated.
You're welcome, Philip. Have a good day.
Okay. Thank you.
Bye.